Imagine you have a notebook where you store all your contacts, names, phone numbers, and addresses. Now, think about your phone's contact list. Both serve the same purpose, but your phone can search, update, and retrieve information much faster. That's because behind the scenes it uses a database. Now, what is a database? A database is simply an organized collection of data. But having data stored isn't enough. We need a way to effectively manage, access, and update it. That's where a database management software comes into picture. It acts as a middle layer between the data as well as applications, users that interact with this data. Now, how do users and apps access this data? Through APIs, application programming interfaces, which act as a communication bridge between the database management software as well as mobile apps, web platforms, or even other systems. So, in simple terms, the database stores the data, the database management software manages it, and APIs allows apps and users to interact with it effectively. Without this structure, retrieving or updating data would be chaotic. Whether you are checking your social media feed, making an online purchase, or even booking a flight, it's all happening seamlessly because of databases, database management software, and APIs working together.
These are different types of databases. In this course, we will focus on relational databases mostly. In relational databases, the data is stored in proper table format like spreadsheets with rows and columns. There are different types of tables, and all of these tables are interconnected with the connections, one to many, many to many. We will discuss this later. And these are some of the use cases or applications of relational databases. For instance, your banking systems, your e-commerce websites, all of them use relational databases. And these are some of these databases that are relational in nature. Having said this, these relational databases are suitable in a certain context. If for instance, if you have a lot of sensors and you get a lot of time specific data which you have to analyze, for example, everything changes in minutes. In such cases, you will use time series databases. Or for example, there is a lot of need to access the data remotely, then you will use cloud databases. According to the use case, you will decide and finalize the database. But one thing that you should remember is, whatever you learn in relational databases, most of the concepts are applicable in other databases as well. In this section, we are going to discuss three fundamental database commands: create database, use database, and drop database. Create database sets up a new database in which we can store data and in the table format. Use database selects an existing database from different databases in order to run subsequent SQL commands. And finally, drop database deletes that existing database and its contents. Now let's run these syntaxes and see how it actually looks in a SQL command. So I am creating this database named SchoolDB. As you are aware, this is the syntax, and once I click on execute, you can see the pop-up message that these commands are executed successfully. And if I click on refresh here, and you can see a new database SchoolDB is created. And if I scroll over this tab, here you can see we are still in school database, and then we are not in the SchoolDB database. In order to move to the SchoolDB database, we need to write a command with use. This is the syntax for that command, and I'm clicking semicolon and I'm executing. And if you see here, if I scroll now,
the database is changed to school DB. And finally, let's check how the drop database functions. Now you can see the school database here, and I am using the drop database function command, and if I click on execute, and if you can see the error that we are using this, and that's why we cannot delete it. So this is something you should remember. Now let's shift this database to use school DB, which is another database, and now let's again try dropping the school DB database. So I am changing to school, and now I am trying to drop school DB database, and I am clicking on refresh. So initially you are able to see the school DB database, and now the school DB database is gone. And so one thing that you should remember here is you cannot drop a database while you are still using that database.
Now let's discuss data types. Data types are fundamental building blocks used to define and categorize the nature of data stored within a database. Each data type specifies the kind of data, the storage size, and how it is used in the operations. For example, in a kitchen, you will never store milk in a spice jar, right? Like that, even in database, you have to store the data in the right data type. You have to define the right data type, and this is the syntax with which you will define the data type of a column in a table. If you see, these are all different numerical data types. These are different character data types: date, time, year. If you define these data types correctly, you will have less errors. For example, if you store a number in a character data type, that is an error, and if you store some letter in a numerical data type, that throws an error. The calculations will not happen properly, and hence using the correct data type improves the database efficiency, it saves the storage space, and also it will enhance the overall database performance.
Have you ever mistakenly entered duplicate IDs or accidentally left key fields empty? Maybe while you are filling some form or entering some data into the Excel. Have you ever faced this problem? And what was the consequence? Most of the times it will lead to confusion in reports, and it will lead to multiple follow-ups, and someone else will manually fill this data, right? How do you prevent these kind of errors? The answer is SQL constraints. These act as gatekeepers, and they will automatically catch these common errors, and this will keep your database orderly and error free. These are some crucial rules which will enforce data integrity and consistency, and eventually it will lead to better accuracy. Now, these are some common SQL constraints. There are few more which we will discuss in the later classes. This not null constraint ensures that there is not a null value in a critical data, and this will avoid incomplete records. And coming to the default constraint, it will automatically fill in some important values wherever there is data missing, right? And this can improve the database's efficiency. And now let's discuss about the unique constraint. It will prevent accidental duplication, and
It maintains data transparency and uniqueness. And lastly, the primary key. We will discuss this in detail, and this is very important concept because we will establish a relationship between different tables with the help of a primary key. And this is the value with which we can uniquely identify each record in a table. This actually combines the not null as well as unique constraints. Now let's see a demo of these SQL constraints.
Now let's discuss the concept of constraints. Constraints are rules applied to the table to enforce data integrity. What is data integrity? For example, when you insert some data into table, it may so happen that by mistake you may not enter the data in the required cell, or sometimes there are some conditions which you mistakenly didn't follow and you enter some wrong value. What it happens is, when you analyze this data, at the end you will get errors because you didn't follow the rules of the columns. So constraint can help us keep these checks in place so that only the right and correct data is getting entered into the table. If there is any error, you will get a notification, or you will not be able to enter any wrong data with the help of these constraints. And let's check in SQL how this works. I am creating a table employee details. And with these columns, employee ID, first name, last name, salary, department ID. And here the constraint that I used is the salary should be greater than 0. Now let's try validating this also. Firstly, I want to enter the data, and adding to what I just discussed, there is not null constraint on the first name also. That means this column cannot be null. This ensures that each row of the employee details table must have a value for the first name, and attempting to insert a null value into this column will result into an error. The constraint on this positive, the check constraint, that salary greater than 0, this constraint ensures that the salary value is always greater than 0. If you try to insert or update a record with salary of 0 or less, the database will reject that operation. Now let's start inserting and check how these constraints are actually working. This is one entry that I am doing. So this data is proper. That means the constraints are not restricting this data. Now let's try entering another data. In this, as you can see, the first name is not entered. The first name is null. And let's try executing this. Cannot insert the value null into column first name. The column doesn't allow nulls. Since we have this not null constraint on first name, we are not able to enter the data. And let's try entering another set of data. And if I execute this, here I tried entering the details with salary is less than 0, and the insert statement conflicted with the check constraint. That the conflict happens because of the column salary. Now this is all about not null and check constraints.
See, this is the sample code which will help us understand the unique constraint. In this case, we have created a table named library books which has 3 columns: book ID, title and ISBN. I have executed entry command, and these are the 2 different books with different ISBN numbers. And now if I try to enter another book with the same ISBN number as SQL basics, this is the kind of error that is displayed. A violation of unique key constraint. Cannot insert duplicate key in the object. This is what happens when you try to add a duplicate entry when the unique constraint is already in place. Now let's discuss about the default constraint and how you write the code for this. Here in this case, I am creating employees table with 3 columns: employee ID, employee name and department, and the default value of the department is general. Now here, as you can see, I have given just the employee ID and the employee name, and here the result in the department column is general, which is the default constraint that we have given. Now for example, if I purposefully enter a value for the department, then that will come here. For example, for Shreya Singh, I have given the finance as the department, and it overrides the default constraint value which is general, and now the department is updated to finance. This is how the default function works. Now finally, let's look at how the primary key constraint functions. So in this code, I am trying to create a table called customers, and it has 3 columns: customer ID, customer name and city. Now the customer ID is the primary key in this case. I have entered 2 records in this, 1001 and 1002. Right now I am trying to enter another record, 1001, which is already entered before. So from the concept of primary key constraint, it should give an error because 1001 is repeating twice. And let's see how this actually works. As you can see, the first 2 rows are entered, which is these 2, and then we get an error message: violation of primary key constraint, cannot insert duplicate key in the object. So this is how all of these constraints function. Next, we are going to discuss the concept of normalization. What is normalization? Why we use normalization in SQL? Various levels of normalization that is possible, and if there are any tools, we will also just look at them, and finally we will summarize the learnings. Now imagine storing the same information multiple times unnecessarily. It will lead to confusion and errors, right? This scenario is precisely what normalization seeks to avoid. Basically, normalization is the process of minimizing redundancy from a relation or set of relations. That means when a data is redundant, it can lead to various anomalies like difficulties in inserting, deleting and updating data. These issues can severely impact data accuracy and efficiency. By reducing redundancy through normalization, databases become more reliable, efficient and easier to maintain. This ensures that the integrity and accuracy of your data remains intact. Now let's discuss anomalies. Have you ever experienced situations where information in your database mysteriously disappears, duplicates, or behaves unpredictably? These incidents are typically due to database anomalies. Now, what is insertion anomaly? This happens when you can't insert data due to missed relevant information, leading to gaps in your database records. Now, when it comes to update anomaly, this happens when updating the same information in multiple rows doesn't happen consistently, creating conflicting data within your database. And lastly, deletion anomaly. Now, in this case, deleting specific data unintentionally removes other important information, resulting in unintended loss of data. Now, these are different common anomalies. Recognizing these anomalies helps you understand why database normalization is critical. Proper normalization addresses these problems, helping you maintain data integrity, accuracy, and reliability of your databases. Now we are going to see an example of insert anomaly. As you can see here, this particular table has 5 different attributes. One is student number, course number, student name, address, and course. Now each row represents a student enrolled in a course, and as you can observe, each student can enroll in multiple courses, right? And what is exactly the insert anomaly here? The key issue is we cannot add a new course unless at least one student is enrolled in it. For example, if you want to add machine learning here, but there is no students enrolled in this particular course, we cannot add this to the table. This happens because course information is actually dependent on the student's enrollment. There is no way to store the details of the course separately if you create only one table like this. Here the key takeaways are that this type of problem can be avoided by using normalization. And a better design would be to have a separate table just for the course with columns like course number, course. This would allow us to add new courses without the constraint of the student enrollment. As we discussed earlier, update anomaly, it occurs when redundant data exists, requiring multiple updates to ensure consistency. Let's see this anomaly with an example. Here in this case, zones has 2 records, and for example, if he moves from Edinburgh to a new address, to correct this table you have to edit here and as well as here. If there is one mistake done, that results in inconsistencies. So what is the key takeaway from here? When data redundancy is there, it increases storage space, there is risk of inconsistency, and also it requires a lot of effort to maintain the data integrity. Now, how can you fix this? Again, the answer is normalization. We have to store the student data in a student table with students' unique details and a separate enrollment table which would have the course enrollments. So there are two tables now. One is student table and the other is the enrollment table. Now you can just update address once here and there is a connection established between these two tables and you need not correct everywhere. This eliminates redundancy and ensures updates happen in only one place, which is in student table. We will look into this in detail also, but try to understand the concept. Now let's discuss the dilute anomaly with an example. Consider student S30. He has enrolled in the course 322, which is maths. If S30 drops from this course and is deleted from this table, the course maths 322, this disappears from this table entirely. We lose all information about the course 322 including its existence, right? And this is problematic because there may be future enrollments but we won't have any course details. We may need course details for reporting or administrative purpose, but they are gone. Why is this a problem? Because now in this case there is unintended loss of critical data. Course information should not be deleted just because no students are currently enrolled. Historical records are lost and also this results in database integrity issues. Now what is the answer? How can we fix this? Again, normalization prevents this issue. We should have a separate course table that stores course details independently from the student enrollment. So in a way we are safeguarding the course details by creating a separate table for it. The enrollment table should link students to the courses but should not be the only place where the course information is stored. So there is some linkage only, but that's not completely in one table. So we are basically creating two tables. This way deleting a student in one table does not remove the course, because this is in table 2 and student information is another table 1 and we are connecting these. We have discussed normalization. Now normalization involves organizing the data into structured tables, right? Now this process is defined by normal forms, which we are going to discuss in the subsequent slides. Now let's discuss the normal form. What is the definition of first normal form? A table or relation is in first normal form if it meets the following conditions. All values are atomic, indivisible. Each column must contain only single values, not multiple values or sets. There are no repeating groups or arrays. Each column should store only one type of data, and each row should be uniquely identifiable. And this is the last condition. Each column contains values of a single type. For example, a column storing phone numbers should not contain addresses. Now let's analyze this with an example. There are two tables here. The problem with the first table is the phone numbers column contains multiple values in a single cell. This violates first normal form as values must be atomic or single valued. Now this is the correct table. We have separated the multi-valued attribute into multiple rows. So here we have separated this into these two rows. Now each row contains only one phone number per student, ensuring atomicity. Now let's discuss the second normal form. As you can see here, this is the definition of second normal form, but let's discuss the different concepts which are required to understand the second normal form. Composite key. What is a composite key? Here, as you can see in this table, student ID is one column and then course ID is another column. Now, both these columns uniquely identify a row. So, we call student ID, course ID as a composite key. Now, let's discuss non-prime attribute. Non-prime attributes are the columns that are not part of the key. So, in this case, student ID and course ID are part of composite key. These three columns are not part of the composite key. Hence, these are non-prime attributes. Now that we learned these two concepts, it is easier for us to comprehend partial dependency. Partial dependency happens when a non-prime attribute depends on only a part of the composite key instead of the whole key. For example, the course name is completely dependent on the course, and there is no relation between the course name and the student IDs. Yes, I agree that a student is enrolled in this, but it is not completely dependent on these two. So that's why there is a partial dependency of non-prime attribute to the composite key. So that is the concept of partial dependency. Now, as you can see here in this table, the second normal form is violated because the problem here is student name depends on student ID and course name depends on course ID. You don't need to know the course to know the student's name, and you don't need to know the student to know the course details, and that's why there are partial relationships here. Now, what is the solution? Here we separate this table into these three tables which are simpler, and each piece of information depends on only one clear key. For example, Alice depends on the student ID, Bob depends on the student ID, and likewise in the course table there is course ID, course name and instructor, and this is the enrollment. So there are some relationships that will be established between these tables and we will get the required details. So as you can see here, in these three tables, each piece of information is stored in the right place. A student name is found in student table and course details are found in course table. The enrollment table only shows the student in which course, right? This way nothing depends on just part of the key, and this is called organization. So the data is very clearly organized without any partial dependencies, and in this case we can say that the data is in second normal form. Now that we discussed the second normal form, we will start discussing the third normal form. We have discussed about the composite key, which is a combination of two columns which will identify a record uniquely. And now let's see the conditions for the third normal form. We say the table is in third normal form when it already satisfies the second normal form and there is no transitive dependency among the non-prime attributes. This means every non-prime attribute should depend only on the primary key and not on any non-prime attribute. We have already understood what a non-prime attribute is. A non-prime attribute are columns which are not part of composite key. Now, let's see transitive dependency in detail.
Transitive dependency occurs when one non-prime attribute depends on another non-prime attribute rather than depending directly on the primary key. In simpler words, if I will discuss this with an example directly. Here, as you can see, there is a table, and in this table we have 4 columns: student ID, course ID, final grade, letter grade. The composite key is, as we discussed earlier, student ID and course ID combination. Final grade, for example, you are a student, you have a role ID and you have different subjects, and you will get marks for each subject. So you get some grade for each subject. And this letter grade, you have a logic which varies from college to college, and based on that logic and rules you will get a letter grade. Because letter grade directly depends on final grade itself, it is independent of course ID or student ID, right? And here in this case, final grade is non-prime attribute, letter grade is also non-prime attribute, and since one non-prime attribute is depending on other non-prime attribute, this violates the condition for third normal form. Now let's see how you can correct this. As you can see here, we removed the transitive dependency, we removed that letter grade, and it can be computed using a simple function. We will see this in SQL hands-on exercises as well. If you have some logic, you will create a measure or some calculated field with which you will be able to get those details. We will see it in Power BI also how to do this. But if you want to have the table in third normal form, this is not required. Now we will discuss voice code normal form. Again, this is another version of or stricter version of the third normal form. It says that every non-trivial functional dependency in a table, the determining set X must be super key. That is, X must uniquely identify each row of the table. I know it is a bit complex, but I will simplify this for you. Let's understand a couple of concepts. What is a super key? A super key is nothing but a column or group of columns which will uniquely identify a row of a table. And the second concept that you need to understand is functional dependency. Functional dependency is if one value of a column is functionally dependent on the other value of in the another column, then we say that there is a kind of relationship. For example, if a teacher recommends a book, textbook, and for different sections, if the textbook is the same and it's not changing, then you say that there is a functional dependency between the teacher and the textbook. On the outside, you can see that maybe they are not interdependent, but whenever a teacher goes to another section, he always suggests that book. You can take many other examples of functions also, but this is a simpler one. This normal form will eliminate such minute dependencies also, so it is very strict. Superficially it may seem not related, but if you observe closely you can find a pattern, and this kind of normal form will further organize the database by eliminating such kind of dependencies. This is a simpler version. And now as you can see here in this table, a lecturer, see if you see Dr. Smith, he recommends book A in fall and he is recommending book A in spring as well. So that is the problem here. The same lecturer, Dr. Smith, always refer book A. So that means there is some dependency that is very clearly evident. And here this lecturer is not a super key. Here the course ID is the super key, right? So that is why this table eliminates the BCNF condition. Now the next question is, how will you correct this problem? As you already know, we will decompose the table into two tables. One is the teaching assignment, the other is the lecturer textbook. Here in this case, lecturer is for this table, lecturer is the super key and textbook is dependent on the lecturer, and here the condition is not violating. To recap what we have discussed, we understood the concept of functional dependency. We understood how the BCNF condition with an example. Now let's discuss the fourth normal form, beginning with an example. As you can see in this table, there are three columns: student ID, sport and language. There is only one student who is playing soccer and basketball and who knows Spanish and English. But there are 4 rows for this. In these rows, the problem is every possible combination of sport and language is happening. Even though the student plays only 2 sports and speaks 2 languages, it has 4 rows. And this is called this is due to multi-valued facets. Being combined in one table. Or in other ways, this is unnecessary duplication. If you don't understand all of these terms, that is also absolutely fine. But this is unnecessary duplication. And that's why the workaround in this case is we will decompose these tables further into 2 different tables. As you can see here in this structure, we mapped student ID and the sport in the first table and student ID and language in the second table. Here in this case, there is no unnecessary duplication. Whatever combination we can do, we will do that in relationships. We will discuss later. And each table has now a simple key, which is student ID, and one independent fact. So this is the fact, and we are not combining these facts, and there is no redundancy. And now that you see in the example and basically practically understood this concept without much jargon, we will revisit the definition once. Now fourth normal form deals with multi-value dependencies, MVDs. So MVD occurs when one attribute in the table can have multiple independent values unrelated to other multi-valued facts around the same entity. Now you see how the general the definition is, but you can simply understand with that example.